Now we are going to start with a 13 group, that is the first group of the P block. So 13 group include these elements. Let us see that it includes boron, it includes aluminium, then followed by gallium, indium and thallium, right? Again, boron B, aluminium Al, gallium Ga, indium In and thallium Tl. So these are the elements, these are called as members of the boron family, because the family name is governed by the one which is present above. So this is the typical boron family. So if we talk about that how they occur in nature, so we see that the boron occur in nature in the form that is orthoboric acid or as borax. Though it has many more form also, but actually just you need to make yourself familiar with 2 or 3 important forms. So boron, the basic form of borons is the orthoboric acid and the borax. Orthoboric acid is H3BO3 and borax is Na2B4O7.10H2O. Second, we have aluminium, right? The ores of the aluminium is the third most abundant metal, right, in the earth crust, and in what form it occurs? It occurs as a bauxite ore or a cryolite. Bauxite is Al2O3.2H2O, cryolite is Na3AlF6. Next is gallium. As compared to allium, the gallium, indium and thallium are present in rare amount. As compared to aluminium, they occur in less abundant. So gallium occurs as germanite, which is a typical complex sulfide ore, that means in which the gallium is present with sulfur and along with that other elements may present like zinc, copper, etc. And indium and thallium, they are very less abundant and they occur as a sulfide ores. They occur in form of combined form, obviously combined to form sulfide ores. Next, if we talk about their atomic numbers, then boron atomic number is 5, aluminium is 13, gallium is 31, indium is 49 and thallium is 81. And you know very well how to write an electronic configuration. If you start filling the shells in an order, then the configuration for boron is 1s2, 2s2, 2p1. This is 1s2, 2s2, 2p6, 3s2, 3p1. Then progressively filling of the another shell, 4s2, 4p1, 5s2, 5p1 and then 6s2, 6p1. But if we talk about the general electronic configuration, this we have already talked before also, it is ns2, np1. In the first filling of 2s and 2p, followed by 3s, 3p, then 4s, 4p, then 5s, 5p, 6s, 6p, likewise you need to fill them. But the general electronic configuration is ns2, np1. And this we have already discussed that the inner core may differ, but the outermost electronic configuration is going to remain same, that is ns2, np1. So now let us start with the physical properties now. So the first property we are going to discuss is the atomic radii. So this is suppose is a 13 group, right? So let us say that this is group 1, this is group 1 and group 2. This is group 1 and this is group 2. That means we will be comparing the group 13 with the alkali and the alkaline group. So if we talk about the size, as we know that as we move in a period, we know that if I will take an example also, like we have lithium, here the member is lithium, then beryllium and here we have boron, right. So if we talk about lithium, beryllium and boron, lithium is with atomic number 3, so configuration is 1s2, 2p1, here it is 1s2, 2s, sorry, this is 1s2, 2s1, this is 1s2, 2s2 and this is 1s2, 2s2, 2p1, right. So as we move in a period, what we see that due to increase in the nuclear charge, right, and decrease in the screening effect, so what happens, because the electrons in the same shell do not screen each other, as you can see that here the shell is going to be same. So therefore they are not going to screen the electrons. So that means screening effect is going to remain same. But we will see that nuclear charge will go on increasing, due to which the size will constantly decrease. So that means if we talk about the size, if we talk about group 13 as compared to group 1 and group 2 in size, so group 13 is small. So you are going to write that they are smaller than group 1 and group 2. The reason being due to increased nuclear charge. Right. Now, if you compare the elements of the same group, like if I'm going to compare the members of the same group, then what I see is that boron is the, like I'm going to write it again. Let us write here. Boron, this is aluminium, gallium, indium and thallium, right? So, as we move down, like if I write the configuration for boron, it is going to be 1s2, 2s2, 2p6, sorry, 2p1. And if I am going to write for the aluminium, it is going to be 1s2, 2s2, 2p6, 10, 11, 12 and 13, 3s2, 3p1. And similarly, if I am going to write for the gallium, it is going to be 1s2, 2s2, 2p, let us write here because it's not clear here, right. So, for gallium, it is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right. 3d10 and then 4p1, right. So, what we see that, like as we are moving down, so as per the expectation, as we know that the shells are increasing, because here the filling of second shell is there, here 3 and here the fourth shell is taking place. So, therefore, due to increase in the number of the shell, obviously the size goes on increasing. This is the expected increase. So, what we see that if we compare between boron and aluminium, boron is smaller and aluminium is bigger. Why? Due to increase in the number of shell. But if you, and the trend must go in the same way as we move down. That means the gallium should be bigger than aluminium and the indium should be bigger than gallium and thallium should be bigger than indium. But actually this doesn't happen like in this way. It doesn't happen in this manner. Why? The reason being that as you move down, then what happened here, like when you move from aluminium to gallium, what change do you observe? Just look at the configuration. Here there is no d orbital and here the filling of d orbital take place. And as you know that due to as the d orbital is bigger in size, as the d orbital is quite bigger in size, so it does not screen well. It does not screen well. Therefore, the nuclear charge will be more in the gallium as compared to aluminium, and due to which gallium is going to be smaller than aluminium. As per expectation, it should be bigger than aluminium, right? But due to because here the filling of the electrons in the d orbital take place, and as we know, d orbital due to its big size cannot screen well. Therefore, the nuclear charge increase, they are held more tightly, therefore, the size becomes smaller. So, gallium is somehow smaller than the aluminium. It is smaller than the aluminium. But the trend follow the same manner as we move down, that indium is bigger than gallium and thallium is bigger than indium due to filling of or you can say due to increase in the number of shell. So, here if you look for the atomic radii and the ionic radii, the one exception comes into notice, that gallium is, as per expectation, it should be bigger, but it is smaller than aluminium due to filling of electrons in the d orbital, and as they are bigger in size, they cannot screen well, therefore the nuclear charge increase and size decrease. But the same trend follow as we move down. Second, we are going to discuss about is the ionization energy, right. You know that ionization energy depend upon size, and size in return depend upon the nuclear charge. That means the one which has high nuclear charge is going to be smaller, right, and it is going to possess high ionization energy. This has to be there, right. So, what we see that, like if we compare their size, what we see that like if we compare the ionization energy, first I am going to compare it with the again group 1 and group 2. So, as we have discussed that boron is smaller in size than group 2, right. So, it should possess high ionization energy. But if we see their electronic configuration, then in this case electron is to be removed from 2s shell, and here the electron is going to be removed from 2p. And if I ask you, then in which case the more energy is required? You can extract an electron from s shell easily or from p. Obviously, you can extract from P easily because S has more penetrating effect, P has less, D again this follows this kind of order. So that means the removal of electron from the P is somehow easy. Therefore, though it is smaller in size, but if we talk about the ionization energy, then boron is going to have lesser ionization energy as compared to beryllium or boron. Because why? The reason being that here the electron is going to be removed from the from the 2p shell, and here the electron is going to be 2s. This I am talking about the first ionization energy. But after that, the ionization energy, if I talk about the second ionization energy, it is obviously going to be higher for the boron because it is smaller in size. Right. Now, it's time to compare the ionization energy between the group members. Now, what is there? That when you move from boron to aluminium, because aluminium is bigger, then if we talk about ionization energy, so its ionization energy is going to be less value, but aluminium is, it is going to be more because it is smaller. And for aluminium, ionization energy will be bigger, will be more. Ionization, again we will discuss it again. I am just going to write it here because it is just all messed up above. So we have this kind of thing, right. So if I compare ionization energy of boron and aluminium, so boron is smaller and aluminium is bigger, so its ionization energy is high and its ionization energy is comparatively low, right. But when I move from aluminium to gallium, we know that gallium is smaller, we have already discussed. So obviously its ionization energy is going to be higher because nuclear charge is more. Here we have already discussed due to filling of d orbital. That means when we move from here to here, there is an increase in the nuclear charge by plus 10 units because filling of 10 electrons occur here. So obviously ionization energy will be high for it. Then as you move from gallium to indium, then filling of d and f orbital both take place, and the charge exceeds by unit 18 units. That means ionization energy is higher again than the gallium. Now as you move from indium to thallium, then it also has d and f orbital which screen less because of their big size or because of their diffuse shape. They cannot screen well. Therefore, here the nuclear charge will increase, and it will increase by 32 units because here the filling of 32 elements will take place as we will move from indium to thallium. So that means ionization energy is going to be highest for the thallium. So like this you need to explain about ionization energy, that when you compare between 13 and the group 2, so it should be less for the 13, but if the first ionization energy is less for the beryllium, that is for the alkaline member. The reason being, there the electron is going to be removed from 2s and here it is going to be removed from p, and as we know that s has more penetrating effect than p, so obviously the energy required will be more for the s case. And if you compare this, as I told you that when we are moving down, there is progressively filling of d and of f orbital is being taking place, which screen very less. So therefore the nuclear charge is increasing as we are going down, like from aluminium to gallium it is increasing by 10 units, and from gallium to indium 18 units, and indium to thallium 32 units. So progressive increase in nuclear charge will somehow increase the ionization energy because they will be more tightly held by the nucleus. Next we are going to discuss about the electronegativity. Electronegativity, you know that it is tendency to attract shared pair of electron more towards itself, and it mainly depend upon size, and size depend upon nuclear charge. The one which is going to possess higher nuclear charge is going to possess small size, and obviously it is going to be highly electronegative. So if we talk about electronegativity, then obviously if you compare the alkaline with this, so because it is smaller, so group 13 is more electronegative than the alkali and the alkaline group because of the small size and increased nuclear charge. But if you talk about the electronegativity in the same group, then boron is smaller, so it is more electronegative than aluminium. But as you are moving down, we have discussed that nuclear charges goes on increasing. So when the nuclear charges goes on increasing, so obviously the size is decreasing. Therefore, the electronegativity character increases down the group. That means first it decreased from boron to aluminium. That means boron, sorry, I am going to write here. Boron is more electronegative than aluminium. But gallium is more, indium is much more, and thallium is more. due to increase in the nuclear charge, as we have already discussed. Next we have is an electropositive character. That is the tendency to lose electrons, right. So this depends upon the ionization energy, which in return depend upon size, and size in return depend upon nuclear charge. So that means higher is the charge, obviously smaller is the size, and high is going to be ionization energy, and electropositive character will be less because it will lose electron with difficulty. So as we have discussed about the ionization energy, that boron has high ionization energy than the aluminium. So electropositive character is more for aluminium as compared to boron. But so we can say that electropositive character increases from boron to aluminium. Then after that we have discussed that nuclear charge is progressively increasing, therefore ionization energy is also increasing. So therefore we will see that there is decrease in the electropositive character. That means tendency to lose electron is decreasing as we are moving down because ionization energy increase, right. So this is all about the electropositive character. Next we have is the density. Density, as we know that if we compare the density of group 13 with beryllium, obviously group 13 is going to possess higher density. But as we move down, then what happened? As we move down, the density as per expectation it should decrease because the size is increasing. But what happens actually, as we are moving down, there is progressively increase in the mass also, and increase in mass is much more as compared to the size. So therefore we know that density is mass per unit volume, that means it is directly proportional to the mass. So obviously I am telling you that there is much more increase in the mass as you go down if you compare it with the size. So obviously mass is increasing, so obviously the density goes on increasing as we move down, right. So the next we have is the melting and boiling point. Melting and boiling point, you know that it depends upon the intermolecular forces, that how tightly they are packed and how much energy you need to provide them. So what we have seen that as the boron is smaller, so obviously the melting and boiling point will be high, but as you move down the aluminium is bigger, so that means aluminium is going to possess less melting and boiling point. As you go down, we have seen that size is somehow decreasing because of increase in the nuclear charge. So obviously melting and boiling point is also increasing down the group because the size they are being, due to increase in the nuclear charge, they are becoming smaller and smaller, and due to their small size, what we have seen that their melting and boiling point is increasing as we move down. So this is all about the physical properties of the group 13 elements.